Poisson's bracket. The definition of Poisson bracket is as follows. Suppose I am taking two dynamical variables, that is u and v. I am considering its Poisson bracket in phase space, that is QP space. Then it will be equal to summation I dou u by dou q, that is derivative of first term with respect to first term, into derivative of second term with respect to second, that is dou v by dou p, minus, now I am changing the order, that is derivative of first term with respect to second term, that is p, into derivative of second term with respect to first term, that is q. This is the definition of Poisson's bracket. That is, for any dynamical variable in phase space, their Poisson bracket will be look like above. Here the dynamical variables are u and v. And what is phase space? Phase space is a position momentum coordinate system, that is QP system. Now, note 1. Under canonical transformation, Poisson's bracket is invariant. What is this canonical transformation? I tell you. Suppose the system is in a certain coordinate system, that is QP. Now we are changing this coordinate system to another coordinate system, that is capital QP. That is from old set of coordinate to new set of coordinates. So I can represent this dynamical variable u in terms of small q and p, and I can convert it into new coordinate system with a canonical transformation. So this transformation is canonical transformation. Don't worry, we will discuss this canonical transformation separately. So under canonical transformation, Poisson bracket is invariant. Note 2. Poisson bracket with the same variable will be equal to 0. That is, I tell you some examples. Now I am going to consider Poisson bracket of Qi, Qj. What will be this one? That is Qi, Qj, Qp. And this is equal to derivative of first term with respect to first, that is dou q by dou q, into derivative of second term with respect to second, that is dou q by dou p, minus derivative of first term with respect to second term into derivative of second term with respect to first term. See, dou q by dou p is 0 and dou q by dou p is also 0. So what we get? We get this is equal to 0. That is Poisson bracket of Qi, Qj equal to 0. That is the Poisson bracket with the same variable will be equal to 0. One more example. Poisson bracket of Pi, Pj. This is a work for you. Please try by yourself. The answer will be 0. Note 3. Poisson bracket of a variable and its conjugate will be equal to 1. I tell you an example. What will be the Poisson bracket of Qp? So Poisson bracket of QP means these are the QP coordinates. Then derivative of first term with respect to first into derivative of second term with respect to second minus derivative of first term with respect to second into derivative of second term with respect to first term. See, dou p by dou q is equal to 0 and dou q by dou p is also 0. And this one, dou q by dou q is equal to 1 and this one is also 1. So what we get? We get this is equal to 1. That is Poisson bracket of QP equal to 1. Another example, what will be the Poisson bracket of PQ? This is a work for you. Find out what happens if we interchange the position of Q and P. Okay, find out what is the answer. Is it a 1 or minus 1? You have to find out. Okay. So in general, we can express this condition, that is Poisson bracket of a variable and its conjugate equal to 1 as follows. That is Q I Pj equal to delta Ij. Here you know the property of delta Ij, that is equal to 0 if I is not equal to j and it is equal to 1 if I is equal to j. This one is a previous set question and I told you Poisson bracket with the same variable will be equal to 0. That is option A is correct and option C is also correct. Now check option B and option D. I told you Poisson bracket with a variable and its conjugate will be equal to delta Ij. So option B is correct. And here option D is not true. And if you solve the earlier problem, I think you identified why the option D is wrong. Because a minus sign is missing in the option D. This one is a previous gate question. And the Poisson bracket between theta and theta dot is. How we can solve this problem? I told you Poisson bracket with a variable and its conjugate will be equal to 1. So here variable is theta and its conjugate will be p theta. And is there any way to connect this p theta with theta dot? See, consider the case of a simple pendulum. For simple pendulum, we know the Lagrangian, it is equal to 1 by 2 m L square theta dot square plus mg L cos theta. So here the generalized coordinate is theta. So the corresponding momentum will be p theta and that will be equal to dou L by dou theta dot and it is equal to m L square theta dot. So we can relate this theta dot as equal to p theta by m L square. Now I am rewriting this equation, that is theta dot equal to theta. I am replacing this theta dot by p theta by ml square. Here 1 by ml square is constant time, so I can take it outside the Poisson bracket. So 1 by ml square into theta p theta. Now apply this condition, that is variable and its conjugate will be equal to 1. So this time is equal to 1. So what we get? We get Poisson bracket of theta dot equal to 1 by ml square. That is option B. Properties of Poisson's bracket. First property, I told you UV QP will be equal to UV capital QP. That is, under canonical transformation, Poisson bracket is invariant. Second property, for same variables, that is Qi, Qj, this will be equal to 0. And for Pi, Pj also, this will be equal to 0. Third property, Poisson bracket of Qi, Pj, that is a dynamical variable and it's a conjugate, then it will be equal to delta Ij. And if it is interchanged, the position of Q and P are interchanged, that is Pi Qj, then this will be equal to minus delta Ij. Fourth one, distributive law. That is Poisson bracket of U plus V, comma W will be equal to Poisson bracket of UW plus Poisson bracket of VW. Fifth property, Leibniz rule. That is UV comma W. Then we can expand this Poisson bracket as first term outside, that is U, and the Poisson bracket of other two, that is VW plus UW of V. Sixth one is Jacobian identity. That is Poisson bracket of U, comma Poisson bracket of VW plus Poisson bracket of V, comma WU plus Poisson bracket of W, comma UV will be equal to 0. Here you can see in each of this term, the UVW is changing in a cyclic order. That is like this one. If this is U, this is V and W, then it changes like this. So here U is outside. So we took V and W. Then next time we took V, then U and W. Then we took W, so we get U and V. Okay. These rules are very important, so don't forget. Okay. Example problem. First one, find the Poisson bracket of x, comma px. Here the coordinates are x and px. So what do you get? This is, here x is a variable and px is its conjugate. So you get 1. Second example, Poisson bracket of x plus y, comma py. So how we solve? We have to use the distributive law. That is, this is equal to Poisson bracket of x, comma py plus Poisson bracket of y, comma py. Here you can see x and py are not conjugate. So this is equal to 0. And ypy are conjugate. So we get this is equal to 1. Third one, Poisson bracket of x square px. How we solve? We can rewrite this equation by using Leibniz rule, that is x, comma px. That is equal to x Poisson bracket of x px plus Poisson bracket of x px x. So what we get? This is equal to x into Poisson bracket of xpx equal to 1 plus Poisson bracket of xpx is again 1 into x. So we get equal to 2x. Then another example, Poisson bracket of x px square. Please solve it. And another one, Poisson bracket of x square px square. This also work for you. Now you just look into the example 3. Here, what is the Poisson bracket? Poisson bracket of x square px, and what we get? We get 2x. See, this 2x is nothing but differential of x square. So there is a trick to solve this kind of problems. The trick. I am considering some examples. So first example is, I want to find out Poisson bracket of x square px. We already know the answer. So here what I am going to do is, I am taking the derivative of this function, that is dou by dou x of x square into Poisson bracket of x px. So this function is a function of x. So I am taking the derivative of that function with respect to x into the Poisson bracket, that is x px. So what we get? Derivative of x square is 2x into Poisson bracket of x px is equal to 1. So we get 2x. Now another example, Poisson bracket of r p raised to n. This is pr raised to n. Then here you can see this is a function of r, and pr is conjugate to the variable r. So what I am going to do? I am going to take its derivative with respect to pr, that is pr raised to n into Poisson bracket, that is r pr. So what we get? We get n pr raised to n minus 1 into Poisson bracket of this is equal to 1, that is n pr raised to n minus 1. Third example, Poisson bracket of x square px square. Here I am going to rewrite this equation, that is x square, you know it is xx px square. And this can be rewritten using Leibniz rule, that is equal to x Poisson bracket of x px square, that is I took this term outside and remaining term inside the Poisson bracket, plus now I am going to make the combination with these two, and I am going to take this outside. Okay, that is Poisson bracket of x px square, and this x is outside, that is x here. Now we can apply our trick, that is equal to x into, here px square is a function of px, so we can take its derivative, that is dou px square dou p into Poisson bracket of x px, plus here px square is a function of px, that is dou by dou px of px square into Poisson bracket x px into the remaining x. So what we get? We get this is equal to x into derivative of px square is 2 px into this term is 1 plus derivative of px square is again 2 px into x px is 1 into x. So what we get? We get this is equal to 4 px x. Actually, to solve this problem, you don't want to do even this much. See, we have two terms, that is one is x square, that is dou by dou x of x square, and other one is px square is a function of px, that is dou by dou px of px square into our Poisson bracket, that is x px. Then what we get? We get 2x into 2px into Poisson bracket of x px equal to 1. So we get 4x px. Fourth example problem. Find Poisson bracket of a vector dot r, comma b vector dot p vector, where a vector and p vector are constant vectors. That is, a vector is equal to I cap a1 plus j cap a2 plus k cap a3, and b vector is equal to I cap b1 plus j cap b2 plus k cap b3. And what is r vector? R vector is equal to I cap r1 plus j cap r2 plus k cap r3. In the case of Cartesian coordinate system, r1 will be x, r2 will be y, and r3 will be z. And what will be p vector? Similarly, we get I cap p1 plus j cap p2 plus k cap p3. Now I want to find out what is this a dot r. A vector dot r vector. So what we get? A vector dot r vector. I dot I is equal to 1. So we get a1 r1 plus a2 r2 plus a3 r3. So I can rewrite this a vector dot r vector as summation I ai ri, where I is from 1 to 3. So what I am going to do is, I am rewriting this equation, that is a vector dot r vector, I know it is ai ri, and similarly b vector dot p vector will be bi pi. And again I can rewrite this equation, that is ai and bi are constant vectors. So constant can be taken outside the Poisson bracket, that is ai bi Poisson bracket of ri comma pi. What is Poisson bracket of ri and pi? It is 1. That is, we get ai bi. Now you can see, we can write a vector dot r vector as this one. Then we can do inverse also. That is, we can rewrite this as a vector dot b vector. So this is the answer. Fifth problem. Find Poisson bracket of p vector, a vector dot r vector all square. So as we done earlier, I am going to rewrite this equation. That is, I am replacing this vector sign by pi comma ai ri all square. See, here ai is constant, so I can take it outside the Poisson bracket. That is ai square into Poisson bracket of pi comma ri square. So that is equal to ai square into, see, this one is a function of r. So I can take derivative, that is dou by dou ri of ri square into Poisson bracket of pi ri. Here this order is very important. Okay, so what we get? ai square into dou by dou ri of ri is 2 ri into Poisson bracket of pi ri is equal to -1. So we get this is equal to 2 ai square ri minus 2ai square Ri. Or we can rewrite this in terms of vector form, that is minus 2 a vector dot r vector into a vector. This one is a previous set question, and given a equal to q1 square plus q2 square and b equal to 2p1 plus p2, and they are asked to find out Poisson bracket of AB. Even they given the notation of commutator bracket, but in the question they are specified it is not the commutator bracket, it is Poisson bracket AB. These two brackets are different. We use commutator bracket in quantum mechanics and Poisson bracket is in classical mechanics. We will discuss more about commutator bracket in quantum mechanics. Right now we are discussing only on commutator bracket, and in the next section I will discuss what is the relation between commutator bracket and the Poisson bracket. Okay, right now they are asked to find out Poisson bracket AB. That is equal to, we can substitute this value of a and b, that is q1 square plus q2 square, comma b is 2p1 plus p2. Now we can use the distributive law, so we can rewrite this equation as q1 square, comma 2p1 plus p2 plus q2 square, comma 2p1 plus p2. And here if you take the Poisson bracket of q1 and p1, you get some value. But if you take Poisson bracket of q1 and p2, you will get 0. Why? Because q1 and p2 are not conjugate, because conjugate of q1 is p1, but here it is p2. So this will be equal to 0. And here also q2 p2 will be equal to 0, because q2 and p1 are not a conjugate to each other. But for q2 and p2 we get some value. So this is equal to, we can simplify this equation, that is Poisson bracket of q1 square, comma 2p1 plus Poisson bracket of q2 square, comma p2. Now we can apply our trick, that is equal to 2 into 2q1 into Poisson bracket of q1 p1, that is 1, plus 2q2 into Poisson bracket of q2 p2, that is 1. So what we get? We get this is equal to 2 into 2q1 plus q2, that is option A. This one is a previous CSIR net problem and is a part C problem. The question is to find out the Poisson bracket, that is Poisson bracket of r vector, comma p vector. How to solve this? So first you have to know what is this r vector and what is its magnitude. What is r vector? We know r vector is equal to x I cap plus y j cap plus z k cap, and what is its magnitude? That is equal to root of x square plus y square plus z square. And what is p vector? Similar to r vector, it is p x I cap plus p y j cap plus p z k cap. And what will be the magnitude? That will be equal to root of p x square plus p y square plus p z square. That is, I can rewrite this Poisson bracket as Poisson bracket of root of x square plus y square plus z square, comma root of px square plus py square plus pz square. Now suppose this is our term A and this is B. Then what is Poisson bracket of AB? The general definition is equal to summation I dou A by dou Qi dou B by dou Pi minus dou A by dou Pi dou B by dou Qi. And for this problem, you know, this R has three components. One is X, Y, Z. And P also has three components. So this is from I equal to 1 to 3. So we get three equations. That is for I equal to 1, that is for X coordinate. And I equal to 2, that is for Y coordinate. And I equal to 3, that is for Z coordinate. And corresponding Px, Py, Pz. So we get three equations for this. That is AB xPx plus AB y Py plus Poisson bracket of AB Z Pz. That is equal to dou A by dou X dou B by dou Px minus dou A by dou Px dou B by dou X plus dou A by dou Y dou B by dou Py minus dou A by dou Py dou B by dou Y plus dou A by dou Z dou B by dou Pz minus dou A by dou Pz dou B by dou Z. So this is first term, this is second term, and this is third term. Now I am going to solve for the first term. So what we get? We know A equal to root x square plus y square plus z square and B equal to root px square plus py square plus pz square. So what we will get? We get substitute in this equation. That is dou A by dou X. That is 1 by 2 x square plus y square plus z square raised to 1 by 2 into 2x. So now dou A by dou X is over. Now we have to consider dou B by dou Px. So into 1 by 2 Px square plus Py square plus Pz square all raised to minus 1 by 2 into 2px minus dou A by dou Px. See, in the A term there is no P terms, so it will be equal to 0. That is, rearranging this equation, what we get? We get x Px divided by root of x square plus y square plus z square into root of px square plus py square plus pz square. Similarly, for second term, we get ypy by root of x square plus y square plus z square into root of px square plus py square plus pz square. And for third term, we get the same relation, that is z pz by root of x square plus y square plus z square into px square plus py square plus pz square. So the total Poisson bracket will be equal to 1 plus 2 plus 3. That is, numerator is 1 is xpx and denominator of all the terms are same. So that is root of x square plus y square plus z square into root of px square plus py square plus pz square. And this is xpx plus ypy plus zpz. So that is equal to r dot p vector by, these are the magnitude of r vector and another is magnitude of p vector. That is, I can rearrange this as r vector by magnitude of r vector dot p vector by magnitude of p vector. So what we get? We get this is equal to r cap dot p cap. These are the unit vectors. So this will be the answer. That is, option B is the correct answer. Matrix method of Poisson bracket. This is the tricky method. By using this method, you can easily solve Poisson bracket problems. And you can reduce the consumption of rough sheet. That is the advantage of using matrix method of Poisson bracket. So here, what is Poisson bracket of two dynamical variable, that is uv? Suppose the phase space is qp, then it will be equal to summation I dou u by dou qi dou v by dou pi dou u by dou pi dou v by dou qi. Now I am going to rewrite this equation in the form of a matrix, that is uv, Poisson bracket of uv equal to, I can rewrite as dou u by dou qi dou u by dou pi dou v by dou qi dou v by dou pi. See, take the determinant of this matrix. What we get? Dou u by dou qi into dou v by dou pi minus dou u by dou pi into dou v by dou qi. See, in the rows, same numerator. And what is the numerator here? The numerators are functions. And in columns, these are same denominator. And what is this denominator? Denominators are variables q and p. That is, see, here it is u. In the same row, same functions. Here v. In the second row, same functions. In the columns, you see qi, same variable. Here pi, same variable. Okay, so don't forget. There will be two type of functions. Type 1 is q is a function of qp and capital P is also a function of small q and p. And second type is q is a function of capital Q and capital P, and p is a function of capital Q and capital P. Then what will be the Poisson bracket of qp? See, here variables are q and small p. Then what will be this value? This will be equal to dou q by dou q, dou q by dou p. In the row, same functions, and dou p by dou q, dou p by dou p. And what will be the other type? That is Poisson bracket of small q, small p. Here the variables are q and p. That will be equal to dou q by dou q, dou q by dou p, dou p by dou q, dou p by dou p. So these are the two types. A small work for you. Earlier we discussed a net problem, that is find Poisson bracket of R vector and P vector. And we solved and we got some answer. Okay, now I introduced a tricky method, that is matrix method. So you please try to solve this problem by matrix method. Okay, it's a work for you. Here I help you a little bit. Here you know the magnitude of R vector is equal to root of x square plus y square plus z square, and magnitude of P vector is equal to root of px square plus py square plus pz square, right? So there are three coordinates or three variables, x, y and z. So we have to construct three matrices, that is Poisson bracket of R, P will be equal to, first matrix will be dou R by dou X, dou R by dou Px, dou P by dou X, dou P by dou Px plus. So one variable is over. Now we have to consider the matrix with the other variable, that is dou R by dou Y, dou R by dou Py, dou P by dou Y, dou P by dou Py, plus one more term is there. So y is over, one more term is there. So you have to construct the other matrix also. Then solve these matrices and find its determinants. Then you get the answer. So please solve it. Example problems. First one is Q is equal to P raised to minus 1 and capital P equal to Q P square. Find Poisson bracket of Q P. That is, what is Poisson bracket of Q P? It is equal to, I am using the matrix method, that is determinant of dou Q by, here the coordinates are Q and P, that is dou Q by dou Q, dou Q by dou P, dou P by dou Q, dou P by dou small p. So what we get? Dou Q by dou Q, that is in the Q there is no small q term, that will be equal to 0. Next is dou Q by dou P. So Q is a function of P. So what we get? We get minus 1 by P square. Now what is dou P by dou Q? This is the P and P is a function of Q. So we get it is equal to P square. And what is dou P by dou P? Again, capital P is a function of small p. So we get 2QP. That is equal to 0 into 2QP. That is 0. Minus into, that is plus 1 by P square into P square. That is equal to 1. Example 2. Capital Q is equal to root 2Q cos 2P and capital P equal to root Q sin 2P. Find Poisson bracket of QP. That is, Poisson bracket of QP with respect to the variables are small q and small p. That is equal to dou q by dou q, dou q by dou p by dou q, dou p by dou small p. So what we get? Dou q by dou q. So it is a function of q, right? So we get 1 by 2 root q cos 2p. Next one, dou q by dou p. So again it is a function of p. So we get minus root q sine 2p into 2. Then next time, dou p by dou q. Here p is a function of q. So what we get? We get 1 by 2 root q sine 2p and dou p by dou p, that is root q cos 2p into 2. That is we get this is equal to cos square 2p plus sin square 2p, that is equal to 1. Example 3. Capital Q is equal to AQ plus BP and capital P is equal to CQ plus DP. Find the Poisson bracket of QP. Please do it. Another example, capital Q is equal to P square plus Q and capital P is equal to small p plus t. Find Poisson bracket of QP. Another example, Q is equal to Q tan P and capital P is equal to log sin P. Find Poisson bracket of QP. So please do all these problems. Equation of motion. And the Poisson's bracket. Let us consider a dynamical variable u and it is a function of q, p, t, that is in phase space. The dynamical variable in phase space. Then what is the time variation of this dynamical variable? That is du by dt. That will be equal to dou u by dou q into dou q by dou t plus dou u by dou p by dou t plus dou u by dou t. You know this term dou q by dou t is nothing but q dot. And we know from Hamilton's equation of motion, q dot is equal to dou h by dou p. And this one, dou p by dou t is nothing but p dot. And again from Hamilton's equation of motion, we know it is equal to minus dou h by dou q. So I can rewrite this equation, that is du by dt equal to dou u by dou q into dou h by dou p minus dou u by dou p into dou h by dou q plus dou u by dou t. Here you see we can write this term as a Poisson bracket, that is we can rewrite du by dt equal to Poisson bracket of u h with respect to variables qp plus dou u by dou t. In classical mechanics, our particle is moving in a phase space. That is a position momentum space. So our dynamical variables are position and the momentum. So what will be the time variation of q coordinate, that is dq by dt. And from the above equation, we can write this as it is equal to Poisson bracket of QH plus dou Q by dou T. If Q is independent of T, that is explicitly independent of T, then this time will be equal to 0. So we get dq by dt, that is q dot equal to Poisson bracket QH. Similarly for P dot, we get Poisson bracket PH. I already told you Q dot and P dot are Hamilton's equation of motion. That is, these two are Hamilton's equation of motion. That is Hamilton's equation of motion in terms of Poisson's bracket. See, the first one is a gate question and second one is a set question. So what is the answer? I think you know which one is the answer, right? Poisson's bracket and constant of motion. I told you du by dt, if u is a dynamical variable, then it will be equal to Poisson bracket of UH plus dou u by dou t. And if this time, if du by dt is equal to 0, then I can call u as constant of motion. And when this du by dt will be equal to 0, there is two conditions. The first condition is if Poisson bracket UH is equal to 0 and dou u by dou t is equal to 0, then we get du by dt equal to 0. This is the condition 1. And another condition is the condition 2. If Poisson bracket u comma h is equal to minus dou u by dou t, then also we get du by dt equal to 0. If any of these two conditions is satisfying, then we can say u is a constant of motion. This one is a previous set question. And see, the question is to find out what is the condition for a variable u to be a constant of motion. So which one? Option D. Okay. This one is another set question and find out the answer. Simple. Do it. Okay. Relation between Poisson's bracket and commutation bracket. The equation of motion in classical mechanics is du by dt equal to Poisson bracket UH plus dou u by dou t. And equation of motion in quantum mechanics is du by dt equal to 1 by I h cross commutation bracket u h plus dou u by dou t, where these are operators. So in quantum mechanics, all the variables are operators. So by looking into this two equations, you can see the relation between Poisson bracket and the commutator bracket. See, this is Poisson bracket and this is commutator bracket, and the relation between them is Poisson bracket UH is equal to 1 by IH cross commutation bracket UH. One example, Poisson bracket of XP, that will be equal to 1 by IH cross of XP, commutator bracket XP. So we can relate this classical mechanics and quantum mechanics by this term 1 by IH cross. So this equation is very important. Okay. This one is a previous gate question, and actually it is a quantum mechanical problem, but we can solve this problem by classical mechanics also. If you know the relation between commutator bracket and the Poisson's bracket, then you can solve it. Right now we discussed about the relation between these two, so we can solve this problem by our classical mechanics ideas. See, the question is to find out commutator bracket of XH. Here you know Hamiltonian of a free particle. See, you know Hamiltonian is generally is total energy, that is kinetic energy plus potential energy. Here they mentioned the particle is free particle. If particle is free particle, the potential energy will be equal to 0. So Hamiltonian is only kinetic energy. That is, we know the kinetic energy of a particle, that is equal to p square by 2m. And here only one variable is given, that is x variable. So it will be definitely px square by 2m. So we can rewrite this equation as h is now px square by 2m. So this is a quantum mechanical commutator bracket, and if you know quantum mechanics, then treat this as operators and solve this problem. But here I am going to solve this by using classical ideas. So what we want to do, we have to convert this commutator bracket to Poisson's bracket. I told you the relation between Poisson's bracket and the commutation bracket. What is it? Poisson bracket is equal to 1 by IH cross of commutator bracket. Right. So commutator bracket will be equal to IH cross of Poisson's bracket. Right. So I can replace all this commutator bracket by multiplying IH cross. So first I am taking these two brackets, that is I am multiplying with the IH cross into x. Here I am leaving this commutator bracket as itself, x px square by 2m. Now again we have to replace this commutator bracket with the Poisson's bracket. So what we get, IH cross x into IH cross Poisson bracket x px square by 2m and Poisson bracket. Right. So this is a constant, this is also constant. So we can take the constant term outside the Poisson bracket. Here 2m is also constant. That is minus h cross square Poisson bracket of x, Poisson bracket of x px square. Here I am taking this 2m outside. Okay, that is minus h square by 2m into Poisson bracket of x into Poisson bracket of x px square. We can use the trick. So what we get? Derivative of px square into Poisson bracket of x px. So we get 2px. that is equal to minus h cross square by 2m into, here we can take the 2 outside, into 2 Poisson bracket of x px. What is Poisson bracket of x px? It is equal to 1. So what we get? We get this is equal to minus h square by m, because this 2 will cancels. So this is the answer. So here we solve the quantum mechanical problem by using classical mechanics. Angular momentum and Poisson's bracket. What is angular momentum? You know, angular momentum is represented by L and it is connected to linear momentum as r cross p. Right. Here we know r vector is equal to I cap x plus j cap y plus k cap z. And we know p vector is equal to I cap px plus j cap py plus k cap pz. So how to calculate this L vector, that is r cross p, that is equal to, I think you know how to solve this problem. It is a +2 level problem. So r cross p will be equal to I j k. Now we substitute the component of r, that is x, y, z, and now we have to substitute component of p, that is px, py, pz. So what we get? We get L vector is equal to I into y z minus zpy, right? Y pz minus z py minus j into x pz minus z px plus k cap into x py minus y px. And we know L is a vector, so it will have different components, x component, y component and z component. That is L vector is equal to I cap lx plus j cap ly plus k cap lz. Now we can compare the coefficient of I, coefficient of j and the coefficient of k. That is what we get? We get lx equal to this term, right? Lx equal to y pz minus zpy, and we get ly equal to z px minus x pz, and we get lz equal to x py minus y px. These are the components of angular momenta. Right. Now the question is how we can remember these equations. I tell you one thing. You know the cyclic order of x, y, z. That is x, y, y, z, then z to x. This is the cyclic order. Please remember this one. So here what I took lx. So what is the next component? It is y. So that is y. Another component is z, that I take as pz minus. Now I am reversing these components. Here it is y, here it is pz, here it is z. Right. Similarly here also ly. Y next component is xy z, z. So z, then another component is, right, x minus x pz. Lz is equal to xpy minus ypz. So please remember these equations. This is very important. In quantum mechanics also, we need these equations. A very important note 1. Function of any angular momentum component, that is Lx, Ly or Lz, in Poisson bracket is to rotate the other fellow in cyclic manner. I tell you an example. Let us consider Poisson bracket of Lxy. Here we know what is the value of Lx. Lx equal to next component is x, next component is y. Y pz minus z py. Now substitute this value here, that is y pz minus z py comma y. Now we can use the distribution law. So I can rewrite this equation as y pz into y minus z py comma y. So this term will be equal to 0. Remaining is minus, we can use the Leibniz rule. So I can take this z outside, Poisson bracket of py comma y plus Poisson bracket of z comma y into py. Here this time also definitely equal to 0. So what is remaining? This equal to minus z Poisson bracket of py y. So what we get? We get this is equal to z. That is Poisson bracket of Lx comma y is equal to z. Now read the note 1. There is the function of any angular momentum component in Poisson bracket. So here Lx is the momentum component in Poisson bracket, is to rotate the other fellow, that is y, right, in the cyclic manner. So here it is x, y, then what is the next term? Z. That is the cyclic order. So we got Poisson bracket of Lxy equal to z. Second example. What is the Poisson bracket of y Lx? Now again, what is the value of Lx? Lx equal to x, y, y pz minus z py. So I am substituting here, that is y Lx, Lx equal to y pz minus z py. By using the distribution law, I can rewrite this Poisson bracket as y comma y pz minus Poisson bracket y z py. Here you can see this term will be definitely equal to 0. And here this minus, using Leibniz rule, I can take Poisson bracket of y comma z py plus Poisson bracket of y py z. Here also y z will be definitely 0. So remaining is minus z y py. What is y py? It is equal to 1. So we get Poisson bracket of y Lx equal to minus z. Here you see this is y x. We know what is the cyclic order? X, y, z. Again x. But here it is yx. It is reversed the cyclic order. So there will be a minus sign. So this will be equal to minus z. Third example. Poisson bracket of Lx, Ly. We know what is Lx. Lx equal to y pz minus z py. And what is Ly? Ly is equal to z px minus x pz. Now we can substitute in this equation, that is Lx equal to y pz minus z py, comma Ly is equal to z px minus x pz. So by distribution law, we can rewrite this as Poisson bracket of y pz, comma z px plus Poisson bracket of y pz, comma minus x pz plus minus z py, comma z px plus minus z py, comma minus x pz. Here in this Poisson bracket, here you can see pz and z is there, that is coordinate and its conjugate momentum is there. So this term will not be equal to 0. And here also coordinate is there, z is there, and its conjugate momentum is there. So this term will not be 0. But check here. Here y is there, but there is no py term. And here x is there, but there is no px term. So this term will not exist. It will be equal to 0. And here also z term is there and its conjugate momentum pz is not there. So when you are calculating this Poisson bracket of this term, this will be equal to 0. So these two terms will not be exist. So the equation reduces to Poisson bracket of y pz, comma z px plus Poisson bracket of minus z py, comma minus x pz. Now expand this Poisson bracket using Leibniz theorem and find out the solution. So the final solution will be equal to, I tell you the answer, it will be equal to x py minus y px. I think you know what is this value. This is nothing but L z. L z is equal to x py minus y px, right? So what we got, Poisson bracket of Lx Ly is equal to Lz. And find out what happens if I am reversing this order, that is Ly Lx. Then what will be the value? Is Lz is positive or negative? You have to find out. It's a work for you. Not to Poisson bracket with scalar equal to 0. That is, I tell you, if we take a Poisson bracket with L square and L vector, so L square is a scalar, then we get it is equal to 0. And another case, if you are taking Poisson bracket of R square and L vector. So here R square is a scalar quantity. Then again we get this is equal to 0. I give you little explanation. Now I am considering the first case, that is Poisson bracket of L square L vector. So I can rewrite this equation as Poisson bracket of L comma L vector. So by Leibniz theorem, what we get? We can write L Poisson bracket L vector plus Poisson bracket L vector into L. I told you the Poisson bracket of a coordinate and its conjugate will be equal to 1. That is xpx equal to 1. And ypy will be equal to 1. That is coordinate and its conjugate momentum. Then only the Poisson bracket will be non-zero. See, here both are L. One is not coordinate and one is not its conjugate momentum. So, this Poisson bracket will be definitely equal to 0. Here, this one is also equal to 0. So, what do you get? You get this is equal to 0. Now, the second one, that is Poisson bracket R square L vector. You do one thing, you try by yourself. So, this is a work for you and find out whether it is 0 or something else. Okay. Now, I am summarizing all these ideas. That is, first one is Poisson bracket of Lx, Ly. This is equal to Lz. Second one, Poisson bracket of Ly, Lz. This will be equal to Lx. Third one, Poisson bracket of Lz, Lx. This will be equal to Ly. That is, the condition is the coordinate will be in cyclic order, that is x, y, z. Okay, this is the order. So, Lx, Ly, then the time is z time Lz, and Ly, Lz, then the other time is Lx. That is the cyclic order. That is, if it is cyclic order, then it will be positive. If it is not cyclic order, then there will be a negative sign. Example, if it is Poisson bracket of Ly, Lx, then it will be minus Lz. Okay, so this is very important. The order is very important. Fourth one, Poisson bracket of Lxx will be equal to 0. Fifth one, Poisson bracket of Ly, y will be equal to 0. And Poisson bracket of Lz, z will be equal to 0. Why? I told you the Lx doesn't contain any px value, right? I think you are remembering this thing. That is Lx equal to y pz minus z py. So when we are taking Lx x, what is the issue? Lx doesn't contain any px term. If px term is there, then only the Poisson bracket will exist. But here there is no px term, so it will be equal to 0. Seventh one, Poisson bracket of Lx, y will be equal to z. Eighth one, Poisson bracket of Ly, z is equal to x. Ninth one, Poisson bracket of Lz, x equal to y. Here also the cyclic order is very important. X, y, z. The order will be like this one. See, x, y, y, z, z, x. Then in cyclic order, then it will be positive. Otherwise, it will be negative. Okay. And last one, that is Poisson bracket of L square, L vector is equal to 0, and Poisson bracket of R square, L vector is equal to 0. Because R square and L square are scalars. Okay, don't forget any of this equation, because we need this equation in quantum mechanics also. Okay, in quantum mechanics, the Poisson bracket will change to commutator bracket. Okay, and all this Lx, Ly, Lz term will be changed to operators. Okay. So these equations are very, very, very important for classical mechanics and quantum mechanics. This one is a set question. See, Poisson bracket of Lx, Lz. So what is the missing term here? That is Ly. But see, these are not in cyclic order. Not in cyclic order, therefore minus. So the option C is the answer. So when solving this kind of problem, you have to check which one is absent. Which component of angular momentum is absent. So write that one here. And check these are in the order, that is in the cyclic order or not. If in a cyclic order, then positive. If it is not in a cyclic order, then negative. So it is a simple problem. And this one is a set question. Yeah, I know. You got the answer, right? This one is a previous gate question. And see, here we have to use the properties of Poisson bracket. That is, we know xpy plus ypx. By distribution law, we can rewrite this equation as Poisson bracket of xpy plus Poisson bracket of ypx. Now we can use Leibniz rule, that is xx py plus x py x plus this term, that is x y p x x px y. Here xx term will be 0, xpy term will be 0, xy term will be 0, and this one only exists, right? So what we get? We get y. That is option B is the answer, right? Actually, you don't want to write this much. You look into the problem. Look into this term. Okay. So here x is there and you check whether there is px is present or absent. If it is not present, then that term definitely will be equal to 0. And here check what are the variables. One is x is there, one is y is there. So check whether there is px is present. Yes, px is present. So this term will not be equal to 0. Okay. That is, if there is a variable is present but its conjugate momentum is not present, then that Poisson bracket definitely will be equal to 0. So when rewriting this equation, see, when we are making combination with x and xpy, that will be definitely 0. Plus, now we have to make combination with x and ypx. So x is there, px is there. So we have to take that combination, that is ypx. Okay, so it is easy. Now we have to solve only this portion. So that is also very easy. So by looking into the problem itself, you can answer this kind of questions. Okay. So please learn to solve like that, because for gate exam it's okay, you get a sufficient number of additional sheets, but for net exam it is limited. So if you can calculate it in your mind itself, then lots of time will be saved and paper is also saved. Okay. So try to solve by your mind itself, or look into the problem and write into the paper only required time, that is like this one. So you don't want to bother about other terms, you have to bother about only this time. So you can easily solve. This one is a previous set question. Here you may be confused about this notation, that is EIJK. I tell you what is this one. The value of EIJK will be equal to positive if it in a cyclic order, that is IJK order. If in a cyclic order, this will be positive and it will be negative otherwise. So I think you can find out the answer, right? This one is a previous CSIR problem and it is a part C problem. So how to solve this? In the question they are given C1 is equal to x2 p3 plus x3 p2 and C2 is equal to x1 p2 minus x2 p1 and C3 is equal to x1 p3 plus x3 p1 and we have to find out two combinations, that is C2 C3, and we want to find out what is its value, and the other thing is we have to find out C3 C1. If we got these two values, we can answer the question, right? So first we have to go to solve for this one, that is C2 C3. So what is C2 C3? We can write this, that is C2 is x1 p2 minus x2 p1 comma C3 is x1 p3 plus x3 p1. Here take this term and first you have to make a combination with this one. See, here x1 term is there and look, here there is no corresponding conjugate momentum, that is p1 term is not there, and here p2 term is there but no x2 term. So this term will not contribute to Poisson's bracket, that is the value of Poisson bracket of these terms will be 0. Now take the another combination, that is this one and this two. Here x1 is there and its conjugate momentum, that is p1 is there. So this will not be equal to 0. So we have to consider the Poisson bracket of this term. Next one, x2 p1 and this one. See, here p1 is there and x1 is there. So this will not be equal to 0. And another term is x2 and x3 p1. Here x2 is there but here there is no p2 term. Here p1 term is there but here there is no x1 term. So the Poisson bracket of these terms will be 0. Now we have to consider Poisson bracket of only two terms, right? That is C2 C3 will be equal to Poisson bracket of this one x1 p2 comma x3 p1 plus Poisson bracket of this term, that is minus x2 p1 comma x1 p3. Now again you consider, see here x1 term is there and p1 term is there. So we have to make combination with the Poisson bracket with these two terms. And here p1 term is there and x1 term is there. So we have to make Poisson bracket with this one. All other combination of Poisson bracket will be equal to 0. So I am taking the other terms outside, that is p2 and x3 outside. So p2 x3 into Poisson bracket of x1 p1 plus here also I am taking minus x2 and p3 outside and Poisson bracket of p1 x1. So what we get? We get p2 x3 into 1 plus minus x2 p3 into minus 1. So what we get? We get this one is equal to p2 x3 plus x2 p3. See, this is nothing but C1. See, the answer may be A or D. All other are, it is minus C1. So our chance of getting the mark is 50% now. Now we have to evaluate for the other term, that is C3, C1. Okay, here it is plus C2 and here it is minus C2. So to identify the exact answer, we have to do this. So we got a Poisson bracket of C2, C3 equal to C1. Now we have to evaluate this one, that is Poisson bracket of C3, C1. So what we get? C3 is equal to x1 P3 plus x3 P1, comma C1 is x2 P3 plus x3 P2. Now again consider first term with the first term. So here x1 is there and here there is no P1 term. Here P3 is there but here there is no x3. So this will not contribute anything. Next combination. Here x1 is there and here no P1. Here P3 is there and here there is x3. So this term will contribute. And next combination is this one. So here x3 is there. See, here P3 is there. So this will contribute. And another one is this 2. So x3 is there and there is no P3. And here P1 is there and here there is no x1. So this term will not contribute. So we can rewrite C3, C1 is equal to Poisson bracket of x1 P3, comma x3 P2 plus Poisson bracket of x3 P1, comma x2 P3. Here also again you check this P3 and x3 will give some value for the Poisson bracket and combination of all other term will be 0. And here combination of x3 and P3 will give some value and combination of all other will give 0. So I can take the other terms outside the Poisson bracket, that is x1 P2 and Poisson bracket of P3 x3 plus again I am taking other terms, that is P1 and x2 outside and Poisson bracket of x3 P3. For classical mechanics, for problems in classical mechanics, the order of this x1 P2 and the P1 x2 is not significant. That is, if you are dealing with the Poisson's bracket, the position of variables we are taking outside the Poisson bracket will not affect. But if you are taking commutation bracket, then the positions are very, very important. Because in quantum mechanics it is operators, that is suppose xp and px are different. Because here x operator is operating on p and here p operator is operating on x. So these are different. So x cap p cap minus p cap x cap will not be equal to 0 in quantum mechanics. But in classical mechanics we can say xp minus px equal to 0. Okay, so this difference is there. So for commutation bracket this position is not that much important, significant, but in quantum mechanics it is very, very important. Okay, so what we get? We get Poisson bracket of C3 C1 is equal to x1 P2 P3 x3, that is minus 1 plus P1 x1 into x3 P3, that is plus 1. So what we get? We get minus x1 P2 plus P1 x1. This is nothing but C2 minus C2, right? Here I made a mistake, that is this is not x1, this is x2 and this is also x2, right? This one is another CSIR net problem, and this question is related to Jacobian identity. What is Jacobian identity? if you are taking a Poisson bracket of A comma BC plus B comma CA plus C comma AB, then it will be equal to 0. So here what we have to find out? We have to find out A comma BC, so this term, and A comma BC, so this term. We have to interchange these terms, but these are the terms we want, and we have to take all other terms to RHS. So we can rewrite this equation as Poisson bracket of A BC plus C AB equal to minus Poisson bracket of B C A. So here we have to rearrange this equation. So we have to interchange these terms. That is Poisson bracket A B C. So on interchanging, this sign will be minus Poisson bracket AB comma C equal to. So now look into the options. Which are the possible options? B and D. But in the option B, one minus sign is missing. But in option D, yeah, you can see we can rearrange this equation. So one more minus will be there. So this time will be equal to plus. That is Poisson bracket C A comma B. So which is the answer? Option